So I'm going to talk about anisotropic sea ice mechanics. So similar themes to some of the talks we had this morning, although a somewhat different approach. I'd like to thank my colleagues who have at one time or another been involved in the work I'm going to present. So here's my talk structure. So I'm going to very briefly talk about climate sea ice models, since we've not had much discussion of that. Then I'm going to spend the majority of my time talking about some simulations we did a few years ago now, a discrete element simulation of sea ice failure, and what insights that gave us for the development of a parameterization of rheology to put into a climate sea ice model. I'll then present, time permitting, some results from that model to show you how it performs. So, modelling sea ice in climate models. Well, we had a bit of motivation for why you'd want to do this earlier today, so I won't talk about the motivation, I'll just talk a bit about how you actually do it. So, practically speaking, all climate sea ice models, that is sea ice models designed to be incorporated into climate models, are continuum models, and they are continuum balances of momentum, mass, and heat. These are the sort of processes that may be inside your climate grid cell, which may be 50 kilometers resolution, 100 kilometers, maybe in 5 years' time, 10 kilometers. So the point is there's a lot of stuff, okay? There's surface processes, basal processes, lateral processes, there's snow, there's sea ice, there's surface melt, there's brine drainage, there's snow ice formation, there's wind drag, there's ocean drag, okay? Oh, and by the way, there's ice stresses, okay? So that's what we're going to be focusing on today, but the point is this is in the context of a lot of stuff. So these fundamental balance equations, momentum, mass, and heat, oops, it's going to come back, I'm sure, okay? These fundamental balance equations are mediated by various processes. And so we tend to divide them, rightly or wrongly, into dynamic and thermodynamic processes. So dynamic processes are things such as the air drag and ocean drag on the ice, how it's vectored around, and of course how it deforms, whether that deformation is out of plane or in plane. And of course the representation of sea ice stress is determined by the rheology, and that will be the focus. But of course there are also a whole bunch of thermodynamic processes as well. And an example of this are surface melt bonds, which have quite a significant impact on the albedo of the sea ice, and brine drainage. So there is as much or more activity in sea ice modelling on this sort of thing as there is on the rheology and momentum balance. Now, of course, this classification is a little bit artificial in that, in reality, processes that occur in the real world tend to incorporate both mechanics and thermodynamics. This is an example of a lead. I hesitate to call this a crack, but let's just say it's an opening, okay, in the ice cover, and you can see it's refreezing. So it's formed divergence. Let's not go there how it formed, okay, but then it refroze, and that becomes a source of ice and also a source of dense brine. As the ice forms, it releases brine to the ocean, which affects the oceanography. But this sort of thing is not explicitly represented in the climate model. All this sort of physics, on the scale of this poor person here, okay, or maybe he's enjoying himself, on the scale up to the grid cell, that's all parameterized. So these things are parameterized. So we gain insight from the physics at smaller scales, and we try to capture the salient properties to stick into the models that can practically be run on climate-like models. So I've mentioned technical constraints, and that is a significant constraint. Okay, so that's so much the preamble. Let's get to the momentum balance. So in all climate-style sea ice models, you solve a momentum balance like so. So air drag, ocean drag, ice interaction force, and other forces which are generally small in comparison. So I've highlighted in pink the ones which are the largest. So air drag and ocean drag could be the subject of a separate talk, which I won't give today. But in terms of sea ice rheology, that's what we're going to focus on. So it's the stresses in the ice pack associated with deformation of the ice cover, whether that deformation is frictional sliding, pressure ridging, or even collisions. So the early sea ice modelers, not the early sea ice modelers, but the first sea ice modelers who started to think of sea ice as something other than a Newtonian fluid, okay, started from this basic premise that the sea ice stress was a function of the deformation of the ice cover, and scalars such as the ice thickness and the ice concentration. Good, that's fine. Okay. So material frame indifference implies the sea ice rheology in this case must assume this form. It's the famous Rhino-Griffin equation. So these eta and zeta are typically called viscosities. P would be the ice strength or pressure term. This term is generally neglected. I can't think of anything, actually, any area where that term is actually included, actually. So the point is the sea ice stress depends upon the strain rate. So the strain rate, the symmetric part of the velocity deformation. And these eta, zeta, gamma, p are functions of scalars and the invariance of the strain rate. So this form is really general. Okay? If eta and zeta are constants, this becomes a Newtonian fluid. So that's the sort of equation used to model the atmosphere and the ocean, but not sea ice. So typically, eta and zeta take nonlinear functions of the strain rate and variance, and typically we describe stress as being plastic, which is where I'm going to get to next. So I'd like to go back to some concepts from the AJAX experiment. That's Arctic Ice Dynamics Joint Experiment, a joint US-Canadian venture, some time ago. So this 1974 paper produced a sea ice dynamics model, okay, based upon theoreticians' understanding and observations in the Arctic. And these are some of their key assumptions behind that model. So they start off with the assumption that sea ice is plastic, so irreversible deformation occurs at a critical stress state. So it's fundamentally different from Newtonian flow. So we've seen this animation yesterday. So it's an animation of satellite images of the Sheba field experiment. Okay, you can imagine it's there. So you start with a squared domain and it deforms into this horrible mess. Okay, and you see these cracks forming. So what this isn't is smooth, continuous deformation. It's not Newtonian flow. So the assumption of a plastic rheology is pretty much spot on, I would say. And everybody treats the ice as being plastic, whether they decide to call it brittle or decohesive or whatever. So the early models assume that sea ice cannot withstand tensile stress. We had an argy-bargy about this yesterday, and the truth is that sea ice can withstand tensile stress. So that was just an assumption made for convenience. Okay. And by the way, I'm now putting up this paper here, okay, not because these are the first guys to realise all these assumptions were correct or incorrect, but just it's the same authors. Okay, Max Kuhn was the first author of this original paper, and like several decades later, he's gone back and said, "Oh yeah, okay, I was wrong about a few things." So sea ice can withstand tensile stress. And this final point, which is going to be obviously the main focus of today's talk, is this assumption of isotropy. So it was assumed that the sea ice cover was isotropic at these sorts of length and time scales. So theoretically that makes a huge difference, makes it much easier. But I'd also like to have a look at the date. Okay, 1974. I was alive, but only just around then, okay, and there weren't the sort of satellite products we have today. Okay, so you went out in the field, you looked around you. Okay, you know, how are you going to know it's not isotropic? Now we have the satellite products, we can tell us that's not the case, but it was a perfectly reasonable thing to be doing. So just to comment on that then. But the point is that the sea ice cover is not isotropic. So we've seen these images. This is RGPS data, and these are sort of like zoomed in images here. Okay, and these have all been half-inched. That means nicked, by the way. That means stolen. Okay, from Erland Scholzen's papers. And you can see that you have oriented features at a range of different length scales. So it isn't really on to assume that the ice cover is isotropic. It looks the same in all directions. So that was the final nail in the coffin, so to speak. So I'm going to, like I said, I'm going to focus on anisotropy. But why? Okay. Well, imagine this red square is the grid cell of a climate model. The dark features in here are thin ice, or even open water, but probably thin ice. So you've got thick ice with striations, lines of thin ice between them. So if I wanted to squeeze this ice, I'd need to work a lot harder to squeeze it in this direction than across those weaknesses. So the presence of oriented weakness features in the ice cover has an impact on the momentum balance. It determines how much force is required to form the ice cover. So that's the motivation for bothering about anisotropy. So now I've motivated the problem, I want to spend a little bit of time describing some numerical experiments which we've performed to try to gain understanding of the way in which the ice cover breaks up into forms. So here are those same pictures I showed you a moment ago, and we heard from Erland Scholzen how he interprets these oriented features as being due to compressive conjugate Coulombic failure lines. And I'm just going to say they're there. Okay, that's the motivation for this thing. And what's interesting is these failure lines are potentially scale invariant. You can see these are different length scales here. Or let's say scale invariant over some range of scales. So just as a quick reminder, and bear in mind I'm not a fraction mechanics guy, but this is the sort of naive intuition I have. This is the Coulomb criterion along a putative failure line. So these are the traction components along a failure line. So this is our domain, our material. Let's assume it's homogeneous. Okay. So these dashed lines are putative failure lines. So along one of these putative failure lines, you satisfy the Coulomb criteria. It's the cohesion. So the orientation of these lines, which this cohesion is first met, is given by 2 theta as being the separation, which is the arctan of 1 over the internal coefficient of friction, or I've tended to call it the shear rupture coefficient. They're the same thing. The reason I've used the shear rupture coefficient is to make it distinct from the friction from cracks that have already formed, from failure lines that have already formed. This is the formation of failure lines, not sliding along existing failure lines. So that was the thinking. Now let me describe the setup. So we used a discrete element model. So this is our domain, our model domain, okay, 400 kilometers by 400 kilometers. Each one of these brightly colored features is a polygon, and they're the discrete elements. And between each of these elements, we have some thin ice freezing those elements together. And that thin ice can undergo elastic, viscous, and plastic deformation. So discrete element models are used a fair bit. So the nature of our experiment was to start off with all these elements frozen together. So you've got the elements frozen together with thin ice between the elements. Then to apply a wind stress and to see how the ice cover fragmented, how it granulated. That's the term granulization. That was the nature of the experiment. So we start with a heterogeneous continuum, all the blocks are frozen together, apply a wind stress, watch how it breaks up. Now, the thing that we did which is different to what had been done before with discrete element models is we incorporated a shear failure mode. So, in the earlier models by Mark Hopkins, you had pressure ridging, you had tensile opening, okay. Once you had a crack, you had friction across the crack interfaces, but you couldn't have the crack form through shear failure. And that was the feature which we incorporated. So, this is what we actually did in the model. And this is a sort of motivation here. So we incorporated a shear failure mechanism. So when the shear stress hit this point, a crack formed. I'll keep on using the word crack, and I'm afraid I'm going to get deep water here, but a failure line, an opening, whatever. Now, this thin ice joining these discrete elements has elastic properties. So what happens is that those critical stresses correspond to critical displacements. So we can have compressive failure, tensile failure, that was, or had already been done, that was old hat, or a shear failure. So when the two elements start to slide beyond a certain point, the ice breaks. So that's what was new. So we stuck that into the discrete element model, initialized it with all the flows being frozen together, and applied a wind stress, and waited to see what happened. And this is what happened. So these regions now are lots of the discrete elements still frozen together. These brightly coloured regions are where all the joints between the flows have broken up, the elements have broken up. So this large blue region, this purple or dark blue, light blue, they're all flows, elements frozen together, and we call those flow aggregates, okay, aggregates of the elements. So, we run the model for a certain amount of time, the failure happens in this way, we can continue applying the wind stress, but no subsequent failure happens. So what we interpret this as being conjugate failure lines in the cover here. And if we look at the PDF, the probability density function of the orientation of the cracks, we see a twin peak situation, okay, where these peaks are oriented at an angle around this stress given by an arctan of 1 over the shear rupture coefficient, or internal coefficient of friction. So great. So Erland was right, okay, fantastic. Coulombic failure is the thing. And I'm not going to qualify that because I think that is pretty much it. that is what we believe to be the case. So naturally we did various model experiments, but let me describe in a bit more detail some of the analysis. So that failure pattern was emergent from the simulations, but we tried to understand where it came from. If we look at the work done between two discrete elements, you have elastic work and shear elastic work. Because remember, you can have elastic sub-failure response. So that's the work done. The Moore-Coulomb criteria, which is in terms of stress, can be translated into displacement because it's elastic, like so. If we substitute this failure criterion into the work done, we get an equation for the work done in the ice between those elements. If we then minimize that work done, okay, so what's the least work you can do before it breaks? We find that the cracks break with in shear, with some shear displacement, but also with some normal opening. So what we have is shear rupture plus some dilation, some opening. That's what we can derive from the minimization of work. And you also see that from the PDF of the failure type from the simulations. This is a rather complicated plot to interpret, but essentially you have a failure regime parameter on the horizontal axis, and the fact we have a peak here corresponds to this failure mode. So the theory, or the theory such as it is, okay, and the simulations match up. And so how big are the blocks? Well, wind drag puts energy, elastic strain energy, into the thin ice between the elements, and we can calculate the size of the flow aggregates that form by equating the rate at which elastic energy is dissipated when a crack forms to the rate at which crack formation happens. And by doing this, we can get an equation for the block size. So it's the elastic distribution of the rate of elastic distribution of stress which controls the size of the blocks. And this is the thing I was having a go at Danny Dumont about the other day. Talk about that later. So another feature from Erland's experiments, which he mentioned yesterday, was to do with the critical confinement. So here, this R is the ratio of the stresses on this domain. For the ratio beneath this critical value, you do have the, failure which is largely Coulombic, but may not look particularly Coulombic, but in a statistical sense it is when you look at the distribution of crack orientations. But once you exceed this critical confinement ratio, it all breaks up into bits. Okay, in our numerical experiment, all the elements break up at their edges. So we start to lose any of these coherent features. Another numerical experiment we did was to blow the wind in one direction, let the cracks form, okay, then turn the wind off and let the joints between the flows start to heal, start to refreeze. And for various degrees of refreezing, we turn the wind back on, but this time at orthogonal direction. So if you look at the left-hand side, so this is, we have a wind in the, let's say the x-axis here, forms these flow aggregates.
And the wind's blowing from both directions?
No, it's uniaxial.
Oh, uniaxial.
Yeah. So wind blowing in this direction, we form these lines with the PDF peaks here, okay? So these are the Coulombic lines associated with the initial stress pattern. We let it heal for a bit, then we rotate the wind. So for small amounts of rehealing, when we rotate the wind, the new deformation occurs in the old cracks. As we let the cracks heal more and more, new cracks will form in response to the rotated wind stress. Until when we let them heal completely, okay, just new cracks will now form in the new preferred orientation associated with the wind stress. So this is what, in the discussion yesterday, Erland gave a thought explanation of what was going on, and I think this kind of demonstrates roughly what Erland was saying. So just let me summarise that before I move on to the large-scale modelling. So we imposed a shear rupture or Coulombic failure mechanism at the flow scale. And at the emergent scale, the scale of the domain, we found these flow aggregates. The floor orientation was determined by Coulombic failure, spaced by elastic redistribution of stress. We tended to find a preferential deformation which involved shear and some dilation, okay, which is a very common feature of granular materials. This last point is particularly important from the perspective of practical sea ice modelling. Okay? Existing flaws, if they're there, will affect whether new flaws form. Okay? If you already have some cracks in the ice cover, they may not be preferentially orientated with the new stress pattern, but deformation may occur through those existing flaws. Okay, so so much for the discrete element model experiments. Now I want to move on to the large-scale modelling, which was the original motivation. So those experiments are very interesting, but of course we're not yet anywhere near at the stage of using that in a climate model. So how can we develop a parameterization of these processes sufficiently simple and sufficiently computationally efficient to incorporate into a climate model? Well, I should say that this is based upon mainly these two papers, but we rooted around for some time before we got to a model that's sufficiently simple. Our first models were far too complex. They got simpler and simpler over time until we've captured the salient features. So this is the nuts and bolts ugly truth of what you have to do when you develop a parameterization of a climate model. So in this case, we want the parameterization to describe the anisotropy and how it evolves with time, and to determine the CI stress. But the practical thing is that it's got to slot into existing continuum CIS models, and it can't cost too much in terms of the numerical cost. Okay? Climate modelers already get into a hissy fit about how much the CIS cost compared to the ocean and the atmosphere. If I were to double the cost of running the CIS model, it won't happen. So it has to be numerically efficient. And of course, what we would like to have as our first point, perhaps, which turns out to be the last requirement, okay, is that we'd like the parameterization to be inspired by physical principles and testable in its details. So this is what we talked about yesterday, trying to go from the small scale understanding, my small scale, not necessarily your small scale understanding of CIS failure, and how to bring up the large scale. So we take as our starting point that we have coulombic failure, and it's already there. We already have coulombic failure. We don't try to simulate new crack formation. Okay? There are cracks. Look, the ice cover is covered in cracks. So we assume that our flows or flow aggregates are diamond shaped, okay, and the diamond shapes are formed from this coulombic failure mechanism. Here is a satellite product of shear stress. You can see, hopefully, the red and yellow lines delineating these sort of large-scale diamond-shaped features. But the point is, we actually put the diamond scale at the subgrid scale. Okay? So this blue square is the grid cell of our climate model. We don't resolve anything inside that box, inside that square. But we assert that it is filled with diamond-shaped flows which have some particular orientation. These flows, okay, are delineated by existing cracks. We're not trying to simulate new crack formation. And the orientation of these flows is given by a structure tensor. Another field of research is something called fabric tensor or various kinds. You generally, in anisotropic materials, you often have a state variable to describe the anisotropy.
Abby?
And your mic is off.
We lost you here.
Oh.
So, yeah, I don't know what happened.
Or me. Can you hear me still?
No, not in the mic.
He ran out of battery.
That sounds like it, doesn't it? Light's gone off. Battery's dead.
Oh.
Hi.
You want me to try and shout, or should we wait?
It's on.
Let's wait, because
Let's wait.
these lectures are being streamed so that people can see them. Is it, okay. Can you hear me now?
Yep.
So what was the last thing you heard?
That the box was that size.
Right, okay, you didn't hear the swearing then. Okay, good. Right. So, we have, so this is our box. We have diamond-shaped flows which we do not resolve. We just assume that they're there, okay? They are formed by existing cracks. We don't simulate crack formation. And we account for the orientation of these diamond-shaped flows or flow aggregates with a structure tensor. This structure tensor in practice just turns into a 2x2 matrix. If the diamonds are randomly oriented, okay, equally randomly oriented, it's the identity matrix modulo a factor of a half, and it assumes extreme values according to whether the flows are oriented in one direction or another. Okay, so that's how we describe the anisotropy, but we've got to let it evolve with time. So we have an evolution equation, and I've written it in a simplified form. This is the co-rotational derivative of the structure tensor, okay, accounts for advection, etc. And we have thermodynamic processes and fracture processes. Melting of flows apart and freezing of flows together is no respecter of anisotropy. Okay? Melting apart, freezing together, the ice cover becomes isotropic. Okay? And this relaxation constant is a function of the freezing or melting rate. It's fracture process that we're interested in. Okay, this is what accounts for the reorientation of the structure tensor. If we apply a new wind stress pattern, cracks will form a new orientation, and the structure tensor will now move to that new orientation, capital S. So this is how we account for the reorientation of the flows within our grid cell. So that's described the anisotropy and how it evolves with time and space. We have to relate the CI stresses to the anisotropy as well. So maybe I won't going to spend too much time on this, but we look at the tractions on the edges of these putative diamonds. Okay, we can have compressive tractions to do with like a so-called ridging force or a sliding traction, and these things we know, they come from the model. Once we know these tractions, we can consider the stress on an ensemble of these diamond-shaped flows. So in this region I've shown here, this line and this line are parallel to the diamond edges. So we know these tractions. We can determine the traction upon an arbitrary orientation using the mean stress theorem. So that's this traction along an arbitrary orientation n. But that is just given by the inner product of the stress with that normal. So this gives us the ice stress term. So this is step 1. Okay, in the other 10 steps we have the form that goes into the model. That's as far as you're going to get today. Okay, this is the principle by which we determine the CI stress from the anisotropy. Okay, so that was the development of the theory, and some 6 years later, okay, it got put into an actual working climate sea ice model. This was Michal Samados, who I don't think is here, myself and Alex Wilczynski. So this model of anisotropy and rheology was stuck into a climate sea ice model called SICE. What we typically find is that the ice cover is anisotropic. That's the red colour. So this variable here is a degree of anisotropy. So blue values of a half indicates isotropic, red values indicate it's anisotropic. We typically find the ice cover is anisotropic, which is in accordance with observations. And this plot shows the shear stress and the compressive stress. And we find that the anisotropic cases, the red colours, the red dots, typically have large shear stresses compared to the isotropic points. In the background you can see a black ellipse. Okay? That is what would correspond to Bill-Hibbeler's plastic yield curve. So we typically find stresses which are much greater shear stresses than using this elliptical yield curve. Okay, so I'm now going to move on to some investigations of this parameterization inside a client model. And this is where I may run out of time, but I'll do my best. So I want to show you some idealized simulations in which this new rheology we developed, which we call the elastic anisotropic plastic rheology, has been incorporated into the SICE climate sea ice model. This is a real sea ice model. It's used by client modeling centers around the world. But we run it on a square domain. Okay, no climate modeling center does that. We run it in standalone mode, so the air and the ocean are imposed. We apply a wind stress and we see how the ice cover deforms in response to that wind stress. So let me describe the wind stress patterns we apply. We describe wind stress patterns like the blue side of this square, okay? So coming from this side and diverging out like that, okay? And we apply wind stress patterns like the red side of this square. 2 sets of experiments. This is for economy that's been drawn on the same square. When we do the blue experiment, we have a wind stress like this, and it's reflected on the other side of the square. When we do a compressive experiment, we do one like this, and we have compression on the other side as well. So we use a imposed ratio of the wind stress components, and we have a ratio of these wind stress components R wind. But this R wind is not the same as the ratio of the stresses inside the ice pack. So this confinement ratio, sigma 1 over sigma 2, those are the stress inside the ice pack. Okay? That's what you want to look at. So we typically find that the blue wind stress pattern results in confinement ratios that emerge from this simulation of around the critical confinement ratio. So this is the point at which shear rupture is still happening just before you have disintegration of the pack. So here's an animation with this pattern of wind stress. Our ratio of internal ice stresses are hovering around the critical confinement ratio. And you see the formation of oriented features. Now let me emphasize that we have anisotropy beneath the grid scale, and we're also simulating anisotropy above the grid scale. So that's a new feature. Most of the simulations you've seen have assumed isotropy beneath the grid scale, and anisotropy has emerged. Here we have anisotropy emerging at the large scale, but we also account for anisotropy at resolutions which are unresolved.
Excuse me, so does the anisotropy that arises, is it similar to the smaller scale anisotropy?
Broadly, you can see the orientation of the diamonds there, and you can also see the orientation of this large-scale deformation features. Okay? In this idealized setup, it does look roughly similar, but that wouldn't necessarily be the case with realistic forcing. Okay, so here are a set of outputs from model experiments with different ratios of that wind stress. So the red experiments have got a confining wind stress, and the internal ratio of stresses in the ice pack typically exceeds the critical confinement. So these red experiments, you see anisotropy at the large scale, but isotropy at the small scale. Okay, because it's all broken up into bits. In the blue experiments, we see anisotropy both at the unresolved scale and also at the resolved scale. So we see these sort of shear failure lines which are reminiscent of the linear chromatic features you see from RGPS data. Okay. So this is going to get complicated in a minute, but I want to show you how the stress confinement evolves with time inside the ice pack in our simulations. The colour here corresponds to different model experiments with different types of wind stress pattern along the horizontal axis. So the blue colours, okay, have this type of wind stress pattern and correspond to stresses inside the ice pack which start off too high, that's initial condition problem, okay, dip, and then evolve to a value which is quite close to the critical confinement ratio. The red colours correspond to convergent wind stresses, and the critical confinement ratio is exceeded, and we typically have out-of-plane failure in the ice cover. So in the blue experiments, where we are in the Coulombic failure zone, we have anisotropy at the subgrid scale forming. In the red experiments, we don't. Then if we look at the histogram of the confinement stresses just by calculating every grid cell and adding them up, we see that for these sorts of wind stress patterns, we find a ratio of internal ice stresses which is below but hovering up to the critical confinement stress. These just show the magnitudes of stress and strain rate, and this shows a PDF of strain magnitude. So we have a sort of, when we consider all the different ranges of deformation that might happen in the pack, we approach something like a power law for the deformation. In the interest of time, I'm going to skip over this and say that we've done it on these idealized domains, great, but that won't cut the mustard for a client modeling center. Okay, we have to run it for the full Arctic. So I want to show you some simulations briefly where we have incorporated our rheology into this sea ice model, ran it for about 35 years, and analysed some of the output. So this is the anisotropy. This is the climatology of different fields. This is the that's the winter thickness. That's the winter alignment, and you can see the ice cover is typically anisotropic, has red colours here, and that's the thickness field. And this is the difference mapped with an older isotropic rheology. That's the main area of difference in the thickness field with the old isotropic rheology. So the force balance has been analysed in these simulations, and it looks much like we would expect it to look. Okay, the purple is the air stress, the orange is the ocean stress, and the green is the ice stress. And we see that by and large in different regions of the Arctic, they assume similar sorts of values. We look at the orientations of the forces, and these are again by and large what you'd expect. Particularly the ice stresses assume rather large values along this region where the ice is being converged. Okay, just to come back to this issue of there being a difference between the anisotropic rheology and the older isotropic rheologies in terms of the ice thickness distribution, particularly in this region. This is a difference of a couple of meters, okay, 1.5 meters or so. So this is enough to care about. So the anisotropic rheology has got thicker ice and slower ice in this region here, in that red rectangle. And the anisotropic rheology also has larger shear strengths in that region, larger shear stresses. So the question we ask ourselves is, if we tuned up the shear strength in the older isotropic model, would we be able to get the same pattern of thickness that we got in the anisotropic model? And I'm keeping an eye on the time, so I won't go into the details, but the short answer is no, you can't. Okay, so you can't just fiddle with existing parameters in the older isotropic model and make it look like the newer anisotropic model. So it's not just a factor of, not just affecting the magnitude of stresses, it's this important feature it's capturing with such larger shear stresses. Just a quick animation at the large scale to show you it can be done. This is just a few days, 10 days or so, but of course we can do this for as long as we want. Okay. And I just want to now look at this. So this is now for the whole Arctic system. Yeah, it's 1 year of data. Okay. So we've looked at the deformation type versus the confinement stress. That's the confinement ice stress, that is. In the EAP model, that's the anisotropic model on the left-hand side, and the older isotropic model on the right-hand side. So this vertical axis describes the type of deformation. Theta is an invariant of the strain rate. When it assumes pi on 2 is pure shear, 0 is uniaxial. It is pure divergence. Pi is pure convergence. Pi on 4 and 3 pi on 4 are uniaxial cases. So what we see is the pattern of deformation is quite a bit different from the pattern of deformation with an older isotropic rheology. And we look at the magnitude of the shear stresses down here, we find shear stresses which is twice as great in the isotropic rheology to the older isotropic rheology. And again, I'll point out this fact. We tend to find a concentration of stress patterns around the critical confinement ratio. Okay, so now I want to conclude. Observations show the ice cover is anisotropic. We've developed a model of sea ice anisotropy based on, or inspired by, let's say simple, maybe not so simple, physical ideas from observations of process studies. This has now been incorporated into a fully working climate sea ice model. Including anisotropy produces a range of different types of mechanical response, which previously you could only get by fiddling around with the plastic yield curve. We don't do this. Okay? This evolves in the simulation. We believe this new rheology gives a better simulation of thickness, distribution, and mass fluxes to lower latitudes and other features also. This rheology is robust. It is now the default choice in our homegrown SICE model. It's incorporated in the latest generation of the SICE sea ice model, which you can download. It is being incorporated, it has been incorporated into the UK Met Office climate model, and also this regional Arctic system model in the US. And it's going to form part of the next UK contribution to CMEP. That's not this coming one, but the one following that, CMEP 7. So we've gone from fundamental study to something that can be practically used. Okay, and with that, I'd like to say thank you.
Questions, comments?
Good presentation, Danny. Thank you. And so when you compare the two, the isotropic and anisotropic, you use your anisotropic model with, and you remove the anisotropy, or you compare with a model that has other differences as well?
Well, no, we don't remove the anisotropy because that's the point. That's what we're trying to investigate.
When you do the old run, the EVP isotropic model, which model is it?
Oh, yes, yeah, I get you now. So we run the isotropic model, okay, and separately run the anisotropic model.
What are the other differences in these models, except for sure the anisotropy? Are there other differences?
Not so many. I mean, all the other aspects of the physics are identical. Okay. If you take the anisotropic model and force it to be isotropic, okay, then it's slightly different from the EVP model, but not very different. Okay, does that answer your question?
Yeah, and following question maybe, can you explain what happens in the Canadian archipelago? You have, sorry.
Yeah, come on, yeah.
You had discrepancies in the north of Canada, but within the archipelago as well, you had huge differences in ice thickness.
Yes,
Can you explain there?
Yeah, sure I can, yeah. So what tends to happen is that in the isotropic viscous plastic rheology, you have thinner ice in those narrow straits, okay, because the ice can deform more easily in response to the imposed stress. What happens in the anisotropic model is that large resistive forces build up in that region, okay, and when you have a favourable wind stress pattern, then the flows will suddenly align, and then the ice can suddenly escape. So it's almost like the flow is plugged up, and then it can suddenly escape. And we actually think this is a good feature for our model.
Yeah, thank you very much, very clear, but still I have one question, is that I think the anisotropy still emerges, because in your, now this is the question, am I right? I mean, in the discrete element model, the single discrete elements, that's just an isotropic model, and then those anisotropic features develop.
Correct.
Yeah.
That's the whole point. Okay. The whole point is in the discrete element model, you start off with you insert no anisotropy. Okay. It starts off isotropic, and anisotropy emerges.
Yeah.
That's the point.
But then that also, I mean, to me, then kind of scaling over huge size ranges turns out to be, to my mind, problematic, because if things like anisotropy emerge, so they are not same features, in fact, in different scales.
Well, okay. Well, there's no reason why there should be. Okay. But the point is that the discrete element simulations provide the motivation for parameterizing the anisotropy beneath the grid scale. Because we see from observations that beneath a scale of 50 kilometers, which is a grid cell size, that there is anisotropy. And that cannot be incorporated in models unless you resolve that, unless you somehow parameterize that anisotropy.
But the anisotropy disappears when you get to the flow scale.
There is no flow scale.
In the discrete element model there is.
In the discrete element model there is, yes. but that's not what we're doing. We're doing a climate simulation.
Danny, do I understand correctly then that, going back to your diamond-shaped features that are moving collectively, that the apex, the angle of the apex is
Yeah.
set by the coefficient of friction?
That's right.
Good. That coefficient does depend, it does vary with
Sure.
the velocity of sliding and bit with temperature.
And do we account for that? You're right.
So the question is,
Yeah.
how sensitive is your analysis to, say, slight variations in that coefficient from 0.6? Take it from, say, 0.8 down to 0.3.
Qualitatively, there's, as long as it's acute, okay, qualitatively there's little impact over a range from, say, a 60-degree internal angle to, say, 80 or 45, okay. Quantitatively, it makes a slight impact on the shear stress magnitude. Yeah. I feel I should, I was inspired by Peter Salmon's talk where he showed William Blake's image of Isaac Newton, and in true traditional fashion, I feel I ought to add to that.
So the driving conditions here are wind.
Yes.
If you ran the same simulation with all the wind that was just reversed,
Mm-hmm.
would you end up with something that looked like just reversing the time on your original simulation?
Well, we haven't actually reversed the time, but we have reversed the wind. And if you reverse the wind, you get a different failure pattern because you've got different stress inside the ice. But it's what you'd expect. Yeah.
Okay. Any other comments or questions? All right. Thank you very much.
So,
Just following the final point, I was personally did all the square model things. If you're thinking about reversing the winds on that square model, that square domain is very much only works for those winds. You have to push everything in, as the boundary conditions are such that if you push it out, it all just goes out, and then it's all the ice is in tension. So
yeah, is that what you meant though? I didn't think you meant that.
Yeah, I wasn't clear on what I meant. Like when you do your simulation, then at the end of the simulation you have something that wasn't there at the beginning of the simulation. And I just want, if you started with the end result, is it just a matter of reversing the forcing?
Not really, because because once the flows of at the subgrid scale, the cracks have formed a certain orientation. Okay, they can't rapidly change.
Right.
They can heal thermodynamically, but that happens on quite a long time scale.
Yes, the time scale.
They can reorient in response to a new stress. So, yeah. Okay.
All right. Thanks.